So what I'm going to look at inside of this video is exponential decay problems in half-life. And exponential decay and half-life problems are pretty much exponential growth problems, except for that our rate of growth is now going to be negative. Okay, that k that we found in our growth problems is now going to be negative. Or when we look at the base of the exponent is going to be less than 1. All right, so they basically run the same way. And in fact, we're just going to use a slightly different notation, but the equation is going to be exactly the same. Right? We're going to use m of t is going to equal m naught e to the kt. Okay? And again, m naught is the initial amount, k is the rate of growth, and m of t is the amount after time t. Okay? Now, let's see, for example, we look at this problem where we say cobalt-60 has a half-life of 5.24 years. So what we need to know is we need to know that half-life means that's where the amount of a sample, okay, goes from its original amount to half of what it was. How long does that take? Okay, so if we wanted to kind of define half-life, it's how long it takes for a sample to cut in half. Okay, so that's our definition of half-life. Now we can utilize m of t in order to find half-life, or we actually have a kind of a special equation that can be used, and I'll use that one for the purposes of this example. So let's find the mass that remains from a 100 milligram sample after 20 years. Okay, so I'm actually going to first start out with the half-life equation, right, in order to solve for my rate of growth. Okay, so we'll call this the half-life equation, and the half-life equation doesn't depend upon the initial amount. So 1/2 of the sample will equal E, and in this case, K times whatever the half-life is. In this case, 5.24. Okay, so all we need to do now is we now need to solve for K. So we use our natural log. So log of 0.5 is going to equal the natural log of E to the K times 5.24. Okay, we'll move the K out using our rules of logarithms. So that gives me K times 5.24 times natural log of E is equal to the natural log of 0.5. Okay, and so then K will equal, well, natural log of E, if you remember, that's going to equal 1. So we'll have K is going to equal the natural log of 0.5 divided by 5.24. Okay, now I'll just put K over here to the other side. So K will end up equaling negative 0.13228. So our equation now for our sample is going to be m of t will equal, and it's 100 because that's our initial amount, e to the negative 0.1328 t. 228 t. Okay, I can actually rewrite this as 100 e to the negative 0.13228, and then to the tth power, and then just by calculating e to the negative 0.13228, okay, what I get is I get 100 times, and it'll be 8.87609 to the t. A couple things actually to notice here. One is that because we know this is a decay problem because the exponent is negative. Okay, so since the exponent is negative on the e, that actually tells me that we're decreasing in size. The other thing is to notice here that our base of the exponent, when we actually transform e to the negative 0.13228, is 0.87609. That's less than 1. Okay, so the sample is getting smaller. That's what that tells us. So now, in order to figure out how much is left after 20 years, I'm just going to find m of 20. So m of 20 is going to equal, it'll be 100 times 0.87609 to the 20th, which ends up equaling 7.09536, and in this case, milligrams. Okay, so that's it. It's actually pretty much the exact same process as when we were doing exponential growth. Like I said, the big difference here, okay, is we have a half-life equation if we want to use that. And then also what we have is we have the value for our base of the exponent is less than 1, or the exponent for the e is going to end up being negative. So just to finish this process, let's take a look at an associated question. At what time will there be only 1 milligram in the sample? Okay, so we know that we have our function, all right? We have m of t is going to equal 100 times 0.87609 to the t. And now we know that we have m of t is going to equal 1. So we get 1 equals 100 times 0.87609 to the t. Okay, divide by 100 to both sides. So we end up with 0.01 is going to equal 0.87609 to the t. Then we'll take the natural log of both sides. Natural log of 0.01 is going to equal the natural log of 0.87609 to the t, okay, which is going to then equal t times the natural log of 0.87609. So our t will end up equaling the natural log of 0.01 divided by the natural log of 0.87609. When we plug that into our calculator, we get t is going to equal 34.8121 years. And that's our solution. So what we've done in both of these exponential growth and decay videos is to show you a general process for working with exponential growth and decay, and to also solve algebraically and review solving algebraically problems that involve exponentials and logarithms. Okay, so this completes the lesson.